line coding. So what is line coding? Basically, line coding is just digital data converted to digital signal. Alright. Line coding is basically sequence of bits converting to digital signal. At the sender part, digital data will encoded into digital signal, while at the receiver part, digital data recreated by decoding into digital signal. Basically, there are two elements, which is data and signal. For data communications, they send data elements, is their main goals. Signal elements, they carry data element, and they are one of the shortest of digital signal. While in carry, data element is what they need to send. In carry, while in signal element, they are what can send and they belong to carrier. Under ratio, data element carried by each signal element is counted as ratio, and there are few graphs for ratio. Basically, there are 4 graphs here. 1, 2, 3, 4. This one is 1 data element per 1 signal. This is for 1 data in this range, while this other signal. Each signal are in each data element. This is 1 data element per 1 signal element, which have the ratio of 1. And the second one, this is data, while these are signals. Each data, they have 2 signals. So it will cost 1 data element per 2 signal with element ratio half. While this one is 2 data element. In 1 signal element, they have 2 data. Actually, here is 1. Yeah, so here is 1 and here is the second one. So this is 2 data elements per 1 signal element. While for this one, they have 4 data elements per 3 signal. So it will become the ratio of 4 over 3 because here are 4 data elements which have elected. So there will be 3 signal elements in these 4 data elements. Although the actual bandwidth is infinite, but the effective bandwidth is finite. When this happens, it will cause lack of synchronization. Lack of synchronization will cause something like this. A graph with like this. One, zero, 1, 1, 0, 1, 0. But when lack of synchronization occur, it will be slow and it will cause this to happen. This will happen 1, and before this it will end 0, 1, 1, 0, 1, 0. And this is the cause of lack of synchronizations. Sometimes, during the event of lack of synchronizations, some data element will be lost, and therefore some data will be not sent. Something like hello, the word will be sent and will become HELL, hell, as a joke.
In this section, we will discuss about line coding schemes. So overall, there are 5 line coding schemes. The first one is called unipolar. The second one, polar. The third one, bipolar, multi-level, and multi-transition. For the second line coding schemes, which is polar. Under polar, there are 3 types, which is NRZ, RZ, and biphase. In these polar schemes, or polar biphase schemes, there are 2 types of schemes, which is the first one is Manchester, the second one is differential Manchester. For Manchester schemes, it combines the idea of RZ and NRZL. The duration of the bit is divided into 2 halves. The voltage will remain at one level in the first half and in the second half, the voltage will go to the other side of the graph. The transition in the middle will provide synchronization. So let's take a look at some of the examples under Manchester schemes. In this Manchester under biphase polar schemes, the voltage will remain at one level, right? And then it will transition to the other level at the middle of the bit. So the duration of the bit is divided into two halves, which is one over here and the second one over here. The transition, this transition over here, it provides synchronization for the graph. The next type of biphase polar schemes is differential Manchester. It uses the idea of return to zero and non-return to zero invert. There is always a transition at the middle of the bit, but the bit values are determined at the beginning of the bit. For example, if the next bit is 0, the graph will transition to the other side. If the next bit is 1, then the graph will stay and go to the next bit. I will show you the examples. So let's take a look at the differential Manchester. So the differential Manchester, as you guys can know, it combines Haziq N and Haziq I, right? So there is always transition at the middle of every bit. In here, here, and here. So the graph will always change in every bit at the middle of the bit. So this white node represent no inversion, which is if the next bit is 1, the black node is inversion if the next bit is 0. So let's take a look at the graph. So the first bit of the graph is 0. So there is an inversion. So the graph will invert itself starting from here, and it will invert to the negative side of the time graph, and then at the middle of the bit it will transition to the positive side of the time, and we will take a look at the next bit, which is 1. So the next bit, there is no inversion. That is why the graph doesn't transition itself to the other side, but it straight away goes to the middle of the bit and changes itself again, because differential Manchester, there is always transition at the middle of the bit, but doesn't necessarily have changes at the end of the bit.
Okay, now I will present to you about bipolar encoding, sometimes called multi-level binary. Okay, so there are 3 levels of bipolar encoding, which are positive, negative, and 0. Okay, the voltage level for one data element is at 0, while the voltage level for the other element alternate between positive or negative. Okay, now I will show you how to draw bipolar encoding AMI and pseudo-ternary. So now I will present about bipolar schemes AMI and pseudo-ternary. Okay, so for the AMI, the bit of 0 will always at 0 voltage, while for the pseudo-ternary, the bit of 0 will be either positive or negative. Okay, let's see. Okay, so for the AMI, the first bit is 0, and then it will be at the 0 voltage, and then first will be the positive. After that, you see the next bit is 0, stay same here, and then the next bit is 1. We see the previous one is positive, then the bit 1 for this one is negative, and then we see the next bit is 0, and then stay just like that. Okay, and then for the pseudo-ternary, the bit is 0, and then it will become positive first, and then 1 will become at 0 voltage, and then next bit is 0. So we see the previous one is positive, and then the negative to the positive, and then next bit is 1, stay, and next bit is 0. So we change to the negative. Alright. Multi-level scheme. So the code designer have classified these types of coding as MB&L. Okay, what is MB&L? M is the length of the binary pattern, while B means binary data, and N is the length of the signal pattern, and L is mean for the number of level in the signaling. Okay, so for the multi-level scheme for 2B1Q, or known as 2 binary 1 quaternary, I will tell you in figure 4.10. The average signal is S equals to N over 4. Okay, this means that using 2B1Q, we can send the data 2 times faster than using NRZL. However, 2B1Q use 4 different signal level. For the first bit is 0, 0, and then we see at the next level, which is positive 1, and then we go to the positive 1, and then we see for the next bit is 1, 1. The previous level are positive, so the next one will become negative 3. So we go down. After that, for the 0, 1, we see at the previous level which are negative 0, 1. Okay, also negative 3, and then we see for the next one is 1, 0, which are positive 1. We see at the negative side, and we go here, and then after that we see for 0, 1 bit, we see the previous level is positive, and then 0, 1 is positive 3. Okay, so basically multi-level 2B1Q scheme, we refer to the transition table, and then that's how we can draw, that's how we can assuming positive original level. 8 binary 6 ternary, or known as 8B60. Okay, each signal pattern has a weight of 0 or plus 1 in DC values. This means that there is no pattern with the weight negative 1. To make the whole stream DC balance, the sender keeps track of the weight. Okay, so let's see in the figure 4.1. Okay, so for the next one is multi-level 8 binary 6 ternary. Okay, this shows an example of 3 data pattern encoded as signal level. The 3 possible signal levels are represented as negative, positive, and 0. Okay, so we see here, the first 8-bit pattern is encoded as the signal pattern negative 0, negative 0, plus plus. So the graph will become negative, then we go to positive, we go to the 0, then negative back, 0, plus, and plus. Okay, so for the second 8-bit pattern is 01010011 is encoded as negative, positive, negative, positive, positive, and 0 with weight plus 1. Okay, and then we go here, negative, and then we go to positive, the negative back, positive, positive, and then 0. Okay, and then for the last one, the third 8-bit pattern, which are 01010000, should be encoded as positive, negative, negative, positive, 0, and positive with weight 1, weight plus 1. Okay, so to create this balance, the sender inverts the actual signal. The receiver can easily recognize that this is an invert pattern because the weight is negative 1. So the pattern is invert before encoding. So it will become, if this is positive, it will negative, then positive, positive, then we go to negative back. 0 still remain the same, and if positive, we go to the negative. Okay, that's alright. So for the last scheme is 4D PIM5, or known as 4-dimensional 5-level pulse amplitude modulation. Okay, the 4D means the data is sent over 4 wires at the same time. The technique is designed to send the data over 4 channels or 4 wires. Now, let's take a look at the figure 4.1. Okay, so for the last one is multi-level 4D PIM5 scheme. Okay, it shows the imaginary 1-dimensional and the actual 4D implementation. Okay, so the gigabit lines use this technique to send 1 gigabit per second data over 4 copper wire. Okay, and then that can handle 125 megabaud. Okay, this scheme has a lot of redundancy in the signal pattern because this one is 2 to the power of 8 is the same with 4 to the power of 4, which means 256 signal pattern. Okay,
Talk
that's
about
all.
MLT3, which is multi-line transmission 3 level, which is actually form of 2 things. It has no major difference between NRZI and Manchester. 2 of the transitions rules are no involve and involve. In this, they have 3 levels, which is positive V, O, and negative V. Okay, they have 3 rules for this. The next bit, the first rule is the next bit is 0. which has no transition. The second rule is next bit is 1, current level is 0 and next level is 0. While the third condition is next bit is 1, current bit is 0 and next level opposite of last non-zero level. For example, I'll demonstrate you this graph. Let us have a look at the typical case first. For the typical case, it starts with 0. It will remain at 0. After that, it raised to 1. After 1, it must be remain because it has some change. Then it will remain at here, although this is 0. When this is 0, it will affect this to come down. And if it's 1, it's changing again. Going down again, 1, remain. Then after it is 0, so it will change. 1, changing again, and 1, and become n. Okay, now let's look at the worst case. It starts with 0 too, but immediately it goes to 1 because it's changing, and keep changing because it's 1, 1, 1 until the end. And it keep changing, 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 and changing till the end.
Okay, for this session, I will show you guys on scrambling. Scrambling has two types, which is bipolar with 8-0 substitution and also high density bipolar. Okay, let us see on how to apply scrambling. Okay, first of all, let us check on how AMI bipolar graphs. The graph will look like this. Okay, as you can see here, the 0 bits remain constant for some time. So the sender will have no problem in knowing on how many bits are going to be transferred. But the problem is the receiver might interpret it differently. This is maybe how the receiver will interpret it. This is 1 bit, 1 bit, 1 bit. Okay, for example, this be K. So the sender is sending 8 bits, but the receiver will receive 7 bits. This shows that is a loss of data. Okay, now let us use bipolar with 8-0 substitution to overcome this problem. The rules on using this depends on this formula. Now let us use the same bits on here. Okay, as you can see that the previous bits is from the positive voltage. So we are going to use this 0, 0, 0, then back to positive voltage, then down to negative voltage, then back to 0, then negative, then to positive, and this is from 1. Okay, you might be wondering on how the receiver will interpret this as 0 instead of 1. So if this is really 1, it will goes down to here as the previous bits is from positive. But instead, it will goes to the positive, which shows that there is the occurrence of violation. So from here, the receiver will know that the bits are transferred using bipolar with 8-0 substitution.
As you already know, line coding can be divided into 3 types, which is unipolar and bipolar. We have 3 other techniques under bipolar, which is AMI, stands for amplitude mark inversion, B8CS, and HDB3. Now we are going to talk about scrambling. Scrambling is a technique to overcome the limitation of amplitude mark inversion, which is not synchronized because they have a long sequence of 0. Since there is a long sequence of 0, there is no transition. Then the signal is not synchronized. No synchronization. So this scrambling technique involves these two, B8ZS and HDB3. HDB3 stands for high density bipolar 3 zeros. HDB3 will replace 3 consecutive zeros, 1, 2, 3, 4, 4 consecutive zeros with B00B or 000B. Here's the example of AMI signal amplitude mark inversion. Since there's a long sequence of 0 and there's no signal transition over here, there will be no synchronization. So to overcome this problem, we have to use either B8ZS method or HDB3. But now we're going to look at HDB3. Okay. There are 2 rules that we have to consider, which is the polarity and the number of non-zero pulses after last substitutions, whether it is odd or even. Non-zero means 1, the number of ones passed after last substitution. When we take this example, we have two non-zeros, which is 1 after the last substitutions, and so 2 is even number. So we're going to look at this row, column. Next, we're going to determine whether the polarity is negative or positive. Since the polarity over here is negative, here is positive, here is 0, and here is negative, so we're going to choose negative and even. So the new signal is going to look like this. Oh, since we have zeros over here, we have 4 consecutive zeros that need to be substituted here and here. We're going to use this HGB3 technique twice. So the polarity is negative. We're going to use plus 0, 0, plus, for which the graph will look like this. Going to put plus. Over here, we're going to put for 0, and another 0, and another plus. So as you can see, this one is 1, 1, and we have positive over here. We have 0 and 0, and this one we have positive again, as to comply with this format. Next, we're going to continue with these 4 consecutive zeros. Since the pulse over here is already positive, we're going to check for this one. We're going to use polarity positive, and since the number of non-zero, which is 1, is still even, we're going to take this format. Negative, 0, 0, negative. So the signal will look like this. Negative, 0, 0, negative. Graph as usual. 0, 0, since there's only 2 consecutive 0, no need to be scrambled. And 1. Oh, and we have another 4 consecutive 0 over here. So we're going to do the same as what we have done over here. There is 4 consecutive 0, and we have to look at the polarity. Okay, since the last substitutions, we have only 1 non-zero, which is odd number of non-zero pulses over here. And we're going to check for the polarity. And the polarity, since the last substitution is here, which is positive, which we are going to consider this kind of format. So now it's going to be 0, 0, excuse me, it's supposed to be 0, 0, 0, positive. 0, 0, 0, positive. And that's it. That is the signal, the final signal graph for this particular AMI bipolar signal over here.